Camera off. So my name is Zach Shvirab-Conti, and I'm a research associate at the Alan Turing Institute here in London. And for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. On a side note, if any of you are interested to share your work within this remit of physics-enhanced machine learning, please do get in touch with us and we can find a suitable slot for you to present at one of our seminars. As for the format of this seminar, Johnny, who is today's speaker, will speak for around 40 to 45 minutes, and then we'll go on to Q&As, either via the chat function or by asking the question in person. So without further ado, I'll introduce John, who is our speaker for today. So Johnny, rather not John, Johnny is a research scientist at the British Antarctic Survey. Previously, he was a postdoctoral researcher at California Institute of Technology, investigating dynamics of earthquakes using cutting-edge machine learning techniques. He received his doctorate of philosophy in geophysics from Hughes Hall, University of Cambridge, investigating geomechanical properties of the Groningen gas reservoir. I hope I pronounced that correctly. With that, I thank you all, and Johnny, you may take the floor.
Thanks so much, Zach. So I'm going to be talking today about physics-informed deep learning for earthquake and polar navigational science. Now, this talk is split into two main sections, the earthquake side and the polar navigational side, but it encompasses a wide variety of collaborators from Caltech, NVIDIA, and Oxford. So just to give that title slide where I show everyone's faces, let me just put this up here. So the first half will be going over some earthquake science background, and this will actually tie quite nicely into the ice navigation because many of the tools are transferable. So in the first half, we'll be going over two main aspects, the understanding of how waves migrate through the subsurface and back projecting to get earthquake locations. So this is work that I did back in Caltech between 2020 and 2022 under the funding of the USGS and Raytheon Technologies. And in the last section, I'm going to go over what we've just started really back at the start of this month, where we're starting to look at nice navigation using cutting edge ML and just kind of give a starting flavor of what's going to go forward in that project. And that project itself is actually funded under the UKRI NERC group and the Alan Turing Institute. Okay, so to give a brief overview of this talk, I'll first go through a section in physics-informed neural networks for solving the Eikonal Equation. And I'll go through what this is and how this is representing the high frequency component of the wave equation. And this is work that was published back in 2020 with the name of the program called EikoNet. The second stage, which is more, it is applied to earthquake location, but the techniques are very generalizable in physics-informed neural networks and other physics-informed techniques. This one, we're using a variational inference technique to do probabilistic inversion. And in this work, this is titled HypoSVI, and this was published in 2022. And again, all the code is available for that. And in the last section, I'll go through some initial results from in-ice navigation, what the problem is that we're trying to address, and leveraging some newer techniques like neural operators. And I'll describe what they are and how they're different from standard neural networks. So just to start off, let's go through the physics-informed neural network side. So I won't dwell on these first couple of slides too much because these talks are all to assume a background of physics-informed kind of stuff. So let's just do some network discussion. So if we want to set up a very simple problem where we want to solve y equals this from some data points, and we select a series of data points, we can set up a standard network that takes in an input of x, has an output of the predicted y, and we have some known observations for the y. So we then minimize the loss, which is the L2 loss of these predicted minus the observations. If we do this for this example, we update the training in this by taking the gradient over the loss relative to each of the weights in the network. So showing this, if this is our function which we wish to learn and we sample from it, we can then recover the blue here with the red showing validation points. But the physics-informed side of things is a bit different. So we can use and leverage the analytical differentiability of the neural network to not only look at the gradient of the output relative to the weights, but also the gradient of the output relative to the input terms. So if we pose the same problem, but now looking at the gradient of the output instead, and then comparing this to some observed gradient values, we can then conduct the same thing, but with a loss that now looks at the gradients and minimize that loss term relative to the waves. So this is the same thing, but now training on the gradients, allowing for an offset shift such that these red points lie on this line. So that's it in its simplest forms. Let's kind of consider it more in a solving of a PDE. So if we had a very simple problem where we have an output or something that we want to learn, in this case t, and we know that there's a physical equation relating that unknown t with some parameter space v, we can take the gradient of the t term relative to a series of inputs x1, x2, x3, to then get these gradient terms, or these partials. And if we know what the observational values for the parameters at the location of x1, x2, x3, we can then minimize the violation to this PDE. So that's moving v on the other side and then trying to get as close as we can to 0. So this is learning on the gradients of the output. And once we've trained this network, we can ditch the right-hand side, and then we know how the inputs relate to this t-term without having to take the gradients again. So why are physics-informed neural networks typically better than stuff like finite element or finite difference? Well, in something like a finite element, the solutions are gridded or meshed, while we can actually formulate these physics-informed networks in a continuous domain problem. So I'll show you how that works in the EikoNet case. The size of the finite element is scaled based on the mesh size, but the scale of a physics-informed neural network is dependent on the network itself. Another thing is the gradients of a finite element are dependent on the mesh that you generate, but the physics-informed neural network is analytically differentiable. So you don't have this coarse nature that you typically see in the finite element, but it's based on the resolution of your training data set. In many cases, the PDE can actually, you can fail in simulations when the PDE breaks down, when you haven't included the boundary conditions, where pins generally seem to smooth out these features because it's not used in these training losses, or it's not encompassed in your training loss. And then in many cases, you do actually have to apply this prior smoothing when you're running the finite elements, which you don't really have to do for the physics informed. But they're not the be-all and end-all physics informed. If anything, they're starting to go out more, and we're starting to look at newer methods like physics informed neural operators. But some of the reasons why these techniques have some issues is you are fixed to a very specific parameter space. If your v term in the previous example varies, then you have to retrain or use some technique like transfer learning to continue from there. There's also that the physics informed only minimizes the violation to the PDE. So that means that you've only truly solved the PDE when all of your training samples equal to a loss of 0. So these are some of the limitations, but generally we see a large improvement over the finite element methods. So that's kind of a background to physics-informed neural networks. So I'm going to go through some work I did back in the 2020s. So this is looking at the Eikonal equation. So the Eikonal equation is the high frequency approximation to the wave equation. So in its simplest form, it's giving the quickest time between some source location and some receiver location, governed by XS and XR. And we can relate this travel time by the gradient of the travel time at the receiver location is equal to 1 over the velocity, so the speed at the receiver location. The added interesting feature about this is that the boundary condition is that the travel time from the source location to itself is equal to 0. So this is just saying that when I travel to where I am, it takes 0 time. So normally in a finite element method, you would have a collection of speeds and you'd roll out in your dynamic space to see how the time changes. So that's how you solve that problem. So to minimize this boundary condition to make our physics informed a bit easier, we can actually put it into the equation by using a factored Eikonal form. So what this is it's basically saying that the total travel time between a source to receiver point is a combination of a linear ramp field, so a distance metric, and the deviation from that distance metric. So that's this T0 term is the distance, and this tau term representing deviation. And then we've got this combined travel time field. And then putting this distance metric back into this and expanding using the train rule, we then have a PDE that takes the form of this. So it's the same as the Eikonal equation, but now with the boundary condition itself. Okay, so that's the PDE that we wish to solve. How are we going to construct a network? So We can train this by collecting a series of source receiver points, and I'll go over the full stages of how we set up the problem in a second, but just describing the network. We wish to learn this tau term, so this is the travel time deviation, and we can use backpropagation to determine the partial of the tau term relative to the receiver location. So this gives us everything that we need on the right-hand side, and we have some observed velocity. So we have, at a given receiver location, this is what the velocity looks like. Just to dive a bit into the network design, it's a standard dense layer with residual block kind of network. The interesting feature to note is, like many physics-involved networks, you should be using ReLUs over, ELUs instead of ReLUs. And the reason for this is you have this singularity effect at a ReLU, that when you take the gradient at 0, you actually have a singularity. So the ELUs tend to train better. We use residual blocks to then, if the problem in question is not as complex as another one, then this allows for that. Okay, so that's the network design. So how do we go about actually doing training? So we sample from a model. So we take a 3D domain of interest. We sample random source receiver pairs, shown by these pairs here. We determine the velocity at the receiver location for these paired samples, and then we save these as the training data. So our velocity model is known to us in this case. And then we can minimize the output from the physics-informed neural network for the velocity relative to our observed velocity through this training loss. And this is determining the predicted velocity. And we compute the misfit and then update the weights across the network. So what do we have once we've trained? Well, we have a network that is able to determine the travel time between any 2 points within that domain, because we're randomly sampling source receiver points. We can then solve the PDE again to get the predicted velocity for that domain problem. So just showing an example of the recovery after training, if we set a single source location, shown here, and a series of receiver locations on a grid, then the white lines represent the travel time fronts, and the color in the background represents the total travel time. So in this problem, we've actually trained with a sharp or fast velocity center, shown by this yellow, and this can be seen in the modeled velocity, as we've seen on the right-hand side. And just to say a bit more about this travel time field, you can see that it's quicker to go through the center, so you've got the travel time fronts kinking back around the edge of the block. So I'll go on to show you some validations of this in a second. But just to say a bit about the computational cost, so once trained, to run this little simulation up here took a total of 40 milliseconds on a standard CPU, and it's about 2.5 milliseconds on a NVIDIA V100. And this allows this very quick recovery with the added features that you get from physics-informed neural networks, like analytically differentiable outputs that you can then use on downstream applications, which I'll discuss in the later section in HypoSVI. But let's see how well this EikoNet, as we call it, does for a series of problems. So let's consider a series of velocities. We have one that's just a homogeneous field, one that's a graded velocity, and I'll go back to show you this in a geophysical case later. But the two that we're most interested in are these block velocity, where there's really sharp contrast, and one where there's a checkerboard. So this is a sharp, high velocity, low velocity contrast. And this is the kind of gold standard to understanding problems in seismology. So if we take two cross sections sliced in the middle of the Z domain and the X domain, we can compare the finite difference solution, the actual velocity shown in the color map, with the neural network output relative to the learned velocity shown by the color map. And then these right-hand sides represent the percentage misfit in the velocity difference. So that's this kind of representation of how well the training is doing. An interesting feature about the Eikonal equation is it's integrative. So there are areas where it does smooth out naturally from the velocity structure itself. But we can see we're doing a very good job. It's able to pick up the sharp contrast with good agreement between the two travel time fields with low RMS. And it does similarly good job for the checkerboard case. You can see it's able to pick up these sharp contrasts and looks very similar. So this is doing a good job at emulating what the finite difference would do for the solving the Eikonal equation. So showing that on a more simple case where we just move the source location around and then do a grid of receiver locations, you can see that it's able to pick out these sharp contrasts as shown here, and also shown in the checkerboard, and it does well even in this simple velocity only varying in the Z direction. But these are only toy problems. In a real world environment, what would the velocity structure look like? Well, in many geophysical applications, you only have a knowledge of the velocity varying with depth. So you say anywhere on the Earth or in the region that I'm looking at, there's not much variation in the velocity and depth. So you have these 1D sections, so only varying in Z. And we train EikoNet on one of these 1D velocities where we have two waves, the P wave and the S wave, where the input velocity model is shown in blue. The recovered predicted velocity from EikoNet is shown by the scatter. And you can see that it does very well training two separate travel time models for both the P wave and the S wave. But the interesting feature is you can also train really complex 3D models. So this is a model from Southern California where we have a really good understanding of the subsurface velocity due to the financial benefit from better understanding earthquakes in the region for structural integrity of buildings. So this is one called the Community Velocity Model from the Southern California Earthquake Center. And you've got these really sharp contrasts from the changing lithology, and you've also got these very shallow scale features that are picked out in the training of EikoNet. So although these are only a slice in this 3D model, and this is a slice in the 1D version of a slice taken in the 3D model trained on the 1D velocity, you can see that EikoNet is doing really well at recovering this velocity model from these sections taken. Okay, so what added features do you also get from using a neural network instead of a finite difference technique? Well, the added nature that you get from other problems like transfer learning. So if we train afresh on this block model, it takes many epochs to then learn the recovery of the velocity field. But if we were closer to that solution, so say the original model was just a homogeneous field, it takes much fewer samples. And these kind of techniques are now being used at Caltech to say, well, actually, we know a bit more about our velocity model subsurface now. We'll just train it a little bit longer with this new information to update EikoNet to actually then be used on more of a real-time sense. So this allows this to be used instead of rerunning all of these new velocity models that would take hundreds of hours normally. Okay, so before I go into the next section, just to give a brief background. So we've shown in the first section that we can construct a physics-informed neural network to solve the Eikonal equation. So this is learning how the travel time between any 2 points within a complex velocity model. So the next stage is, well, given that complex velocity model and a series of observations, can we back project the travel time to a singularity point or to the point of an earthquake? So just to go into this section, we need a little bit of background into Bayes' theorem, and we can briefly separate this up into a likelihood function, which we want to use. We want to learn the posterior distribution for the earthquake location. So this will be determining its position and the uncertainty in that position from the observational data. And throughout this case study, we'll be using a uniform prior, so samples drawn randomly within the region in question. So the likelihood functions that we'll look at is if we have a earthquake arrival at a observational station, then the time that it arrives is called TOBS. And we can say the same at another station, that's another TOBS. So we can then predict the travel time from that station to a given location subsurface and then compare the predicted versus the observation, and we want to minimize this likelihood function. But the interesting thing is you can do that, but you don't know the origin time of the earthquake. And if there's a strong outlier that you haven't accounted for in the variance, then it can actually bias this distribution. And I'll show that in the next slide. So the other way that we can do it is look at differences in observations. So if we've got two stations on the surface where we see a travel time arrival, we can then say, well, what's the differences in those time arrivals? And then look at the differences in the predicted time through the subsurface. And I'll describe this more in a bit in a second. So the top rows here represent the RMS, so this Gaussian distribution, so this term here, and the lower represents the right-hand side. So the good thing about the Gaussian is it takes quite a standard form. It's non-convex, it's convex. So it's very good and very easy to learn through typical techniques. But if you have a single outlier or a series of outliers, you can start to bias this distribution. So another method is to use this equal differential time where you're looking at stacking hyperbola shells. And then a single outlier acts to not bias this whole distribution. But the issue with using these methods is they're highly non-convex. So using typical MCMC or very standard variational inference techniques makes this very hard to sample and actually get that, that distribution or that posterior back. So we want to go through a method where we can actually sample this posterior distribution for a selection of points. So if our series of points are represented by red, we want to move these points so that they approximate posterior. So the conventional schemes that you could use is Markov chain Monte Carlo, where you simulate a series of these points to approximate the posterior, but you'll need a large number of minimal samples. It's slow and it's not so good on these really non-convex space problems. You can also use maximizing a posterior. That's fast to converge, gives you a local optima sometimes, but it doesn't give you any quantity of uncertainty assessment. And then some of the conventional variational inference techniques, you can use samplers to do it, like Q theta here, but they're typically assumed by the user to be Gaussian, and then you're just minimizing that KR divergence. So instead, we want to come up with an approach where you can directly minimize the KR divergence between the points and the posterior, but not taking any assumption in the form of the sampler, but by updating the sampler through a gradient descent, minimizing the KR divergence. And I know that's a lot of terms said in one sentence, so let's think of that in more of a slight mathematical way, and this will be my worst mathematical page throughout this talk. So we have a series of sample points, and we can update the position of those points by minimizing a perturbation, by perturbating the points in the direction that minimizes the KR divergence. So this is like a gradient descent, but in the particle position. And what is this direction that minimizes the KR divergence? Well, it's a combination of the optimization to represent the posterior plus a repulsive term between all the particles, such that they don't collapse to a local point. So to show this in another way, if we started with a series of random grid points here, we'll optimize these points such that the density of these points represent the posterior which we wish to find, as shown by the points here. So thinking of this another way is these methods are very good for multimodal distributions, where in this problem here, we have 6 equal Gaussians. If you took a map value, you would pick one randomly. But if we do a collection of points that we're updating, then these are where the points are finalized at the end of training. And then the density of the points represent the posterior distribution shown by these contoured map on the right-hand side. The other good feature about this is you can actually update as your posterior space is changing. So in this case, the points are updating to represent the posterior, even though the posterior is dynamic itself, which is even neater. Okay, so how does that hold with our question that we wish to solve for earthquake location? Well, we can sample a series of random points within our domain, and our domain being this physics-informed neural network, which I discussed in the first section. And we want to optimize these points such that their density represents the posterior of the earthquake location. So we'll take one of these points. We can then say, what is the travel time through our model to each of the observation locations? Minimize the likelihood function, which is this double differencing of the observations, and then perturb those points and update their locations such that they start to approximate posterior until we get to a final case here where the optimal value is represented by the star, so that's the most likely location, with the distribution of the points representing the uncertainty in the earthquake location. So just showing that another way, this is an update of a specific earthquake. So you can see we start off with random points. The contours represent the expected posterior. So you can see it's doing very well, and it starts to home in on the final solution with a little judder up and down. So I won't dwell too much on this because this slide was originally meant for a geophysical community, but we use other machine learning techniques to determine the arrival of an earthquake on seismic instruments called seismometers. And we then want to combine this with these travel time models to get the earthquake location. We want the hypocentre, so that's the location, its uncertainty, its predicted time of arrival, its origin time, and the uncertainty in the origin time. And when I mean origin time, I mean the point at which that earthquake occurred in the subsurface. So we do this for Southern California. So we have 2,500 stations, each recording data, constantly streaming out hundreds of terabytes of data. And then we pick the first arrivals where we see an earthquake. We then back project it through these physics-informed networks to then generate this map here. So this is using a 1D velocity model that I showed earlier in the 3D, but each one of these red stars represents a earthquake location. So you can see they're very similar. 3D does slightly better at associating some of these features down here. So what would this, for example, show? Well, this is our paper from 2020, where this is a fault plane unzipping, shown in the left-hand side. And what's happening here is it's a natural fracking. So you've heard that from an oil term, but this is for fluids already coming off the subsurface. They've got into this fault plane, and it's like when you unzip your zipper, it's these micro cracks and emanating out from a central point. So you've got a diffusive process driving earthquakes, and then it ended with a very large magnitude 3 earthquake in this problem. So getting a better understanding of better locations of earthquakes are imperative for understanding the dynamics of earthquakes. And the other neat feature that comes out of this all is because these methods are very different to MCMC, and you can leverage the analytical differentiability of pins, you can actually see the scalability of this problem is linear, almost linear past a certain point. So what I'm saying here is, as you increase the number of observations that you have to back project, you don't drastically affect the time for computation. And since this work has been completed, there's a group continued from Caltech to reduce these time for processing further. Okay, so that's a background to the earthquake seismology side of things. So in the first section, we've got a pin. So that's describing our forward model. And we've got our inversion model representing this update of these particles known as Stein variational gradient descent. So the last section is, how can we leverage this on a completely different problem, but still hold a very similar staging environment, or how we'd assess the problem. But since doing the physics-informed neural networks, the general community has changed quite drastically. So people are starting to move away from using physics-informed neural networks, which are tied to only a single parameter space, to using stuff like neural operators. So I don't really have the time in this talk, and I would love to talk more about neural operators and how that community is drastically changing, and how there's so many publications coming out very quickly in that. But just to give a background, in this case of a physics-informed neural operator, instead of putting the parameter space into the loss function itself, we can consider this as also going into the training of the operator itself. So in this problem, this is our PDE that we wish to solve, but we won't just give it a collection of a single parameter space, we would give it a collection of a family of parameter spaces. And what the neural operator is acting to do is learning the functional mapping between the input locations and parameter space to the output solution. And the neat feature of neural operators, you don't actually have to do this physics informed. You can train it on pre-existing models that you've run. And that's what I'll be showing in the next stages. But in the long run, we want to start to look to use stuff like physics-informed neural operators. Okay, so just a summary of that. Physics-informed neural operators can be used to solve multiple parameter systems, to give the solutions to those parameter systems. And the way that you can consider this is like, what additional benefits would you gain over a physics-informed neural network? Well, there's a recent paper back in 2021 that's actually shown that it not only minimizes the violation to the PDE, but it gives the solution to the PDE. And that was a lovely paper by Kambachi in 2021. There's also, you can actually train this on finite element and finite difference models, but get super resolution as an output, because you've got this functional space mapping. And again, as I said, I'd love to talk about neural operators more, but some of the limitations that currently stand, and hopefully these will starting to be improved through network changes, is that running physics-informed neural operators are much more computationally expensive than pins. They tend to be trained initially on pre-existing models, but then updated to kind of do the physics informed at a later stage. So you get most of the way there and then apply physics informed later. So this is just going a little background to neural operators, but I just want to give a flavor of where this is as of last year. So these are fantastic papers from the adaptive dynamic neural operators and the forecast net So this is showing the era 5, kind of updating the lead time in the forecasting. So this is the neural operator. This is the predictive model that it's trained on. So you can see it's doing an amazing job at quite a high lead time. Okay, so what are we planning on using it for? What have we started using it for, I should say? So we've got the polar vessel, the icebreaker polar vessel, RRS at David Attenborough, has an interesting problem. When you navigate into ice fields, it can get stuck and it can be using a lot of fuel during that period of being stuck. And it also causes risk that could affect the crew. So to meet this net zero goal, we want to reduce the fuel usage of the SDA. And we've got many projects ongoing here into route planning and long distances. But in this case, we're looking solely at, in a changing dynamic condition of sea ice, what would be the optimal route you take? And how could that route be changing with forecasts? So how would you look at this? Well, you can say that we have a satellite image, we have the ship in that image, and we have some vessel speed. Let's initially assume that the color of the image directly maps to the vessel speed. And I'll show how later you can actually determine this from basically inversion through the networks. So the first thing we want to look at is how does the speed relate to the transit time? So we want to learn an operator that maps from this speed space to the transit time. So very much like the EikoNet that I originally showed, where the contours are representing equal travel time. And we want to learn it for any of these ice conditions. So what I'm saying here is if we give it a new speed map, I want to be able to immediately return a transit time in that speed map without having to run the simulation. So as a starting point, we're considering that the map itself isn't changing in time, but we started to consider how that speed will vary or how your model dynamics could vary and how this could affect transit time. But running these simulations on a high resolution grid currently would involve something like Dijkstra or solving the Eikonal, and is quite computationally heavy when you're running a real-time kind of system. So we want to be able to emulate this vessel speed to this transit time and then use that for downstream applications. So we want it to be differentiable. It must be learned between the two. And ideally, if we can get a higher scale resolution than what we're training on using super resolution through these operators, even better. So what we're starting with is we're considering Gaussian random fields as parameter spaces. We run a simulation for the Dijkstra equation to determine the transit time through these random fields. So the blue regions represent areas that are inaccessible, the contours represent the transit time, and the color map represents the deviation of that transit time. So this is our training data set. We put in our parameter space and we want to get a solution that looks like this. So we train across many different parameter spaces. So once you've done the training, what you have, and I'm sorry, this is quite a small plot, is you have your input parameter space, the real solution, the modeled recovered solution, and the misfit, like before. And we need to do more network design on this to improve. But you can see it's starting to even get there after a small number of training data sets. And then this is the validation. So it's never seen this parameter space, and it can get most of the way there for the solution. So although I showed you this picture before, this is actually, although we trained on a Gaussian random field, this is showing that we can actually infer on a SAR image that we turned into a vessel speed map. So the cool thing about these neural operators is you can train on most of the parameter spaces and give it a brand new unseen environment and get most of the way there. So this does a very good job at recovering what the transit time would be, even though it's never seen something as complex as this image. And you can see this in the fact that it's got this slow speed here and it's kinking back these travel time fronts. And the other cool thing is because this is so quick to recover across, you don't have to run the forward simulations. You can actually just say my parameter space is moving and I want to recover the quickest travel time inside that parameter space. So this is run at real time. We make the parameter space and pass it across the network to get the solution. And then the next stage, or where we're starting to go to next, is because these are differentiable, we can actually say, well, given a ship route, that wasn't at the time that it took along that ship route, and those weren't the speeds that I was taking. So you can reinforce back into your speed map to say, oh no, you gave me the wrong speed map. It should have looked more like this, using techniques like normalizing flows. And even later along, we could then say, well, actually our mapping from the SAR data to the speed was wrong. So we can actually improve the mapping between the SAR data and the speed map. So I know that was a bit of a talk that encompassed many different things, but the three take-homes from this is physics-informed neural networks seem to do very well at learning these complex, dynamical, high-frequency representations of the wave equation. The added neat feature that you get from these can be used in probabilistic inversion. So something like the earthquake location demonstrated that because it's analytically differentiable, you can do these techniques like Stein variational gradient descent. And although the field is changing and physics-informed neural networks are more changing towards physics-informed neural operators and similar, we can still leverage similar techniques from other projects to apply to new problems, things that many people across the Turing do nowadays. So with that, I'd like to end. Is there any questions?
Thank you so much, Johnny. That was extremely fascinating. Yeah, as you said, if there are any questions, please go ahead and ask. Got a few claps there. In the meantime, oh, we had a comment from John. It says that the neural operator sounds like monads.
What is a monad?
In functional programming, monadic systems are ones where you can bundle up a collection of functions in another function, and then it will return you a new function. It's a little bit like a generalization of currying. So there are some machine learning packages now in things like ML related programming. So rather than using, PyTorch or TensorFlow or whatever. I just know people who work on them. It's not my area. I love your talk, by the way. Sorry, fantastic talk. I know the physics a bit, not very much, but I understood the application was very cool. So that was really cool. This is just a programming suggestion. So if you look up monads, you'll see. But if you're using conventional languages, it's not helpful, I'm afraid. If you were using a newer language like maybe Julia or ML, or Camel or Haskell, it would be a direct application. It would just simplify some of the codes. It wouldn't change what the neural operator stuff did. So that was really sweet the way that worked out. So thank you.
Okay, thanks for that. I'll have a look into those.
Thanks for your comment, John. Somebody said, Anmar said, thank you. I didn't realize where I could find the paper at GitHub model. Can you please share the links?
That's all right. Could you repeat what they said?
Oh, sorry. He says, I didn't realize where I can find the paper and GitHub model. Can you please share the links?
Okay, sure. Is it easier to send that after the talk?
You can, or I believe on the, I'm going to have a quick check on the advertisement on the website. There should be your poster, which I believe had. Okay.
Yes, I'll just go back to that slide and say a bit more.
I'm sorry, no, I thought there was a link, but there's none. Yeah, I'll share the links after the talk. That's all right.
Okay, so all my GitHub pages are with the GitHub handle Ulvetana. That's ULVETANNA. Or you can search these two names: EikoNet for the Eikonal one and HypoSVI for the earthquake location. And if you go through those GitHub pages, you actually get collabs that you can run all the code yourself. Yeah. Thanks
a lot. We have a comment from Dimitra. She says, thank you. Can you comment on the training? How many runs did you use for the EikoNet? How does it compare with neural operators?
So currently, to my knowledge, I'm a bit out of this field because I left seismology like a year ago now, but the Eiko neural operator hasn't actually been done. So my old supervisor moved on to doing the full waveform inversion. So you run the acoustic wave equation using neural operators. The training for this problem to actually cast it as a neural operator in a physics-informed neural operator sense was very difficult. And we were trying to press out a paper in 2021 to do that, where we trained from afresh using a physics-informed neural operator. But the gradients across the networks in PyTorch were so computationally expensive. And the other group at Caltech that was doing the same did it where they pre-trained most of the way and then just did the final updates using the physics-informed neural operators. And that worked much better. So you can actually guide it to a solution that you've run in a finite difference and then just do the final training in the physics-informed. And that's the way that I would suggest. The training for these networks, there was a good example. Sorry. Here, so for the 1D velocity model, took 10 minutes on one of the free GPUs on Colab. So I think that's a P100. And then the 3D model took an hour and was trained after 100 epochs. So that was trained after 10 epochs. But the neural operators have demonstrated that the training compared to pins is much shorter. So that epoch time may be much lower in neural operator tested.
Thank you very much. Just before I take Marcus's question, so Matthew, if it's okay with John to share the presentation,
Yeah,
then I'll upload it to the website and I'll put the link. I'll leave the link right here. We have our website is sort of very temporary, and we're hoping to have a more official website in the coming months. So do bear with us. So the slides will be uploaded to the specifically attached to Johnny's talk. So Marcus, would you like to ask in person?
Hello. First of all, thanks, Johnny. That was super interesting. Really interesting to see like the same sort of aspect of physics informed machine learning, but applied to like 3 different ways, but in a very similar field. Pretty cool. I had a question on something involved in the HypoSVI. So
sure.
For the estimation of the posterior density, and it was like the particle density to try and mimic that posterior density there. What stops these particles just all forming to the center and then you essentially just get map again? Do they is it kind of like a particle swarm where they know where the other particles are and stop that, or?
Exactly. Yeah. So the actual running of this method called Stein variational gradient descent isn't really feasible when you do finite difference, because you have to get these gradients of the particles relative to each other. So the added nature that you have from a pin is to get those analytical gradients is very cheap. So you can actually determine these repulsive terms. So let's see if I can find one in this example that runs. When the particles get close to each other, they actually add this repulsive kind of force. So the particle can't collapse in on itself or with another particle.
Mm-hmm.
So it's this secondary term is adding that kind of effect that doesn't make them collapse.
Okay, yeah. And this is only really made possible with the fact that you're doing it with a pin, so that you've got the full continuous gradient. Okay, yeah.
But you can get that added feature from, as I keep going on about these operators as well, because although the operator is recovered on a grid, it can be resampled on a higher resolution grid. So, and the gradients of the field at a given location through the network are analytical still. So you can still get these analytical gradients, which is quite neat.
Oh, okay, that's really cool. That's interesting. Thank you.
Right. I have a question in the meantime. Might be the last question. There's plenty more time actually for more questions. So I was wondering if there was any way to recover an interpretable sort of state operator from the embedded layers of the pins. That would sort of, one issue with the pins is that it's not extremely interpretable, right? So I was wondering if there was a way to kind of recover that governing state space from the pins, or whether, related to this question, whether you've explored sort of decomposition methods as a way of solving this particular problem, especially the first problem you discussed, the EikoNet.
So we tried some other kind of, see if I can go back a bit. Go back to here. So we tried many kind of network architectures and to see how things were changing and also changing the activation functions. So we tried to deconvolve each layer out and saying, well, what do you not learn when your network isn't got enough parameters to represent? And it's really interesting when you solve this problem, you can see some of the features of how it's learning in the misfit space. So if you change the activations to a ReLU, it looks like an interpretive kind of arc, sharp boundaries, because you've got these very sharp contrasts in the velocity, the recovered velocity space. But with the ELU, it's kind of got this nice smooth kind of texture. So as you're adding more features in, you tend to be resolving different wavelength features better. So you get very close to a smooth version of your solution first. And then as you train further, you're getting this very sharp kind of boundary. But the PDE for the Eikonal is interesting in the sense that it naturally smooths itself. So the form that it takes is it's a smoothed representation because you're integrating. So in some of these cases, you don't actually fully recover really sharp representations, even if you run a finite difference or finite element. And there's many groups now looking at using these kind of methods to do seismic tomography to get much higher resolution subsurface models. But hopefully that was answering your question, but in a bit of a...
Thanks. Yeah, I know it was a very sort of wide question, but so I appreciate that answer. We do have another question. So Matthew says, do you use neural networks as well for the first time break, picking on the observed data sets before feeding them into the neural network?
Let me see if I can. No, so the neural network is trained completely random from a starting point. So we start with the idea that that neural network has random weights and biases, and then we start to train solely on the PDE alone. So we don't use any pre-existing model outputs when we're training. So we were just saying, this is the PDE in problem. This is my velocity model that I want you to solve. Here's loads of random source receiver pairs in a continuous domain, solve those PDEs for those points. And we've actually, just as I was leaving to come back to the UK, they were looking at applying a training data set that's constantly updating. So you don't actually have to have a pre-existing training data set. You just randomly select at the point of when you're training on each batch. So the cool thing is with these is you don't actually, the training data set is a bit based on your parameter space only. It's quite cool, but it does hold in a continuous nature. And when you get really short source receiver distances, that picks up some of this resolution. So you can actually use dynamic sampling to actually improve some areas in the training in the model. This is really neat. Hopefully that kind of, that was also a roundabout way of answering that question. I'm sorry.
No, thanks a lot, Johnny. So we still have some more time. If not, we can sort of wrap it up here. Thanks a lot for all the lovely questions. Oh, we have another question from David. Sorry. Go ahead, David.
Hi, Johnny. Thank you very much. It was very interesting presentation. Just again, reiterating on the EikoNet, on the physics in neural network. Is the training based only then purely on the residuals, or you also had some collocation points with where you apply some supervised learning as well?
So the loss function itself is only on the residuals. The input is the position of the points in the space. So it has an interesting feature that you're hard encoding into this continuous domain where those points were relative to that loss term. Think of another way of saying that. So if you were to train this model with a biased training data set, where you had far more points around the edge of this sharp velocity contrast and fewer around the inside, you would actually do a better job at training in fewer epochs, because you yourself have actually said, oh, this is the velocity model that it looks like. You don't need to relearn in these really homogeneous areas. So just learn on the areas where there's a sharp contrast. So hopefully that answered that.
Yeah, okay.
Thanks, David. Thank you. So I was curious, Johnny, as opposed like at the British Antarctic Survey, do you get to go on site?
Yeah, so we were on the ship back in November, and we've got a route planner being put into operational hopefully this year, end of this year, so hopefully going south. But the rollout of the next stage of the in-ice navigation is we're trying to leverage neural operators to say, we don't really know what the ice conditions could look like. We've got 1,000 different models. Let's roll out all the possible paths that you could do in those 1,000 models and get an uncertainty estimate. And then you could say, well, if you went this way, there's an 80% chance that you're not actually going to get there. So don't do it.
So, yeah, do you actually get to be sort of testing your own model as you go? Fantastic.
Yeah, so we got lots of data coming off the ship as well. So we can start to reinforce the data from the ship into the models in a kind of digital twin kind of scenario. It's quite cool.
Very, very cool. All right. If there are no more questions, we can wrap this up. Okay, Johnny, thank you so much. That was really, really cool. And if that's all right, I'll ask you to share the slides with me, and I'll share them with everybody else.
Sounds good.
Thanks to all for joining, and see you guys next time in 2 weeks' time. Have a good day.